Welcome back. Lesson 9, where one backend becomes many. In the last lesson, every request went to a single server. Today, we fix that with the upstream block. We'll cover 4 pillars: naming a pool of backends, picking an algorithm like round-robin or IP hash, layering in health checks, and finally tuning with waits and backup servers for failover. By the end, you'll have the same load balancing pattern Netflix and Amazon use, just at a saner scale. Here's the roadmap. 4 ideas that cover roughly 95% of real load balancing setups. First, the upstream block, a named pool of servers you point proxy pass at. Second, the algorithm, round-robin by default, least con when request times vary, or IP hash when you need a client to stick to one backend. Third, health checks via max fails and fail timeout, giving you free fault tolerance with no extra component. And fourth, fine control, waits for uneven hardware, and backup servers that only wake up when the primaries are down. Let's make that concrete. 1 Nginx out front, 4 backends in the pool, and at any moment, each backend sits in one of 3 states. Numbers 1 and 2 are healthy, answering quickly so they get full traffic. Number 3 is degraded, still returning 200s, but at 850 milliseconds it's clearly struggling, so it stays in rotation but slow. And number 4 refused the connection, so Nginx marks it down and skips it entirely until fail timeout expires and it's worth retrying. So how do we actually declare that pool? It's just 2 pieces. At the HTTP level, you define an upstream block, give it a name, and list your backends. 1 server per line. Then in your location, proxy talk pass to that name instead of a URL. That's it. Servers can be IPs, DNS names resolved at startup, or even Unix sockets on the same host. Adding or removing a backend is an edit and a reload. No app code, no DNS tricks. Once you have a pool, Nginx asks, how do I pick which backend gets the next request? You get 3 built-in answers. Round-robin is the default. Just rotate through, and it's perfect when every request costs roughly the same. Least con picks whichever backend is currently juggling the fewest connections, which shines when request times vary wildly, like database queries. And IP hash pins each client to the same backend by hashing their IP, useful only if you're stuck with in-memory sessions. Rule of thumb, start with round-robin, reach for least con when latency is uneven, and treat IP hash as a legacy crutch. Now, distributing requests is only half the job. What happens when one backend dies? The good news, open-source Nginx already handles this for free with passive health checks. It simply watches real traffic, and if a backend racks up, max fails errors within the fail timeout window. Say 3 failures in 10 seconds. It gets benched for 10 seconds, then quietly retried. No sidecar, no probe endpoint, no cron job. And for manual control, you've got down to drain a server for maintenance and backup to hold a server in reserve until every primary is gone. So let's put it all together into something you'd actually run in production. 3 primary backends, each with passive health checks. 3 strikes in 10 seconds and they sit out. 1 backup server waiting in the wings for the day everything else burns down. We're using least con because real backends have uneven response times, keep alive 32 to reuse connections, and the same proxy headers from Lesson 8 so your apps still see the real client. Honestly, copy this, swap the IPs, ship it. Now, the reason this same config scales from 2 backends to 200 comes down to 3 quiet truths. First, algorithm choice matters less than you think. Round-robin is fine until you've actually measured request time variance, so don't tune what isn't broken. Second, failure isn't an edge case, it's Tuesday. Max fails and fail and timeout turn every crash, blip, or deploy into a routine the system just absorbs. And third, skip the active health checks. Real traffic is already telling you which backend is healthy. Passive checks watch that traffic for free, and you avoid the classic trap where your synthetic ping passes, but real requests are failing. So here's your cheat sheet. 7 directives that cover roughly 95% of upstream decisions you'll ever make. 2 of them you'll use on every single config. Server, obviously, and keep alive, because reusing idle connections to your backends saves a real chunk of TCP setup overhead. Max fails and fail timeout belong on every production server. The rest, least con, IP hash, wait, backup, are situational tools you reach for when the scenario calls for them. Print it, pin it, move on. Time to put hands on keys. 3 drills, all running on your VM with Python's built-in http.server faking out a backend fleet. First, 2 backends on ports 3001 and 3002, curl 6 times and watch round-robin alternate. Second, kill one and watch Nginx detect the failure, mark it down, and recover it on its own. Third, add a backup server that sits idle until both primaries die, then quietly takes over. By the end, you'll have built real, automatic failover from scratch. Once you've got it working, here's how it breaks. 5 mistakes that look fine in staging and bite in production. Hard coding IPs in proxy pass skips failover entirely. IP hash behind a CDN pins everyone to one backend because every client looks like Cloudflare. Max fails a 1 means a single GC pause marks a healthy server dead. No keep alive burns milliseconds on TCP setup for every request. And wait without real measurement just overloads your weakest dependency faster. Recognize the symptom. The fix is right there beside it. And that's lesson 09. You've gone from a single backend to a fleet, upstream blocks, 3 algorithms, passive health checks, and the traps that keep them honest. Scaling is now a config change, not a code change. Next up, SSL and TLS with Let's Encrypt, free certificates in 60 seconds, a proper HTTPS server block, and the redirect that makes it all click. See you in lesson 10.